train efficiently using GPU, parallel compute, with lots of local data. Right? We provide a lot of examples to get these models to learn the right mapping between inputs and outputs, and that's fine if you can afford to collect these huge data sets, but it can be expensive, especially if you're targeting kind of applications that are not necessarily mainstream. And that's the kind of things that we work on in my group. We work a lot in applications in the physical sciences. We have a big project going on trying to use AI and machine learning to improve battery technologies. We're doing real-world experiments. It's a closed-loop system where there's an AI platform that decides the experiments to do, collects data, refines the hypotheses, decides on new experiments. But the experiments are expensive. They take months to complete. And so getting labeled data is very, very hard, expensive, and so you can't really afford to use standard techniques. We do some work in healthcare, trying to quickly use Raman spectroscopy to come up with much faster ways of identifying different kinds of blood infections. Again, that's a situation where getting labels, especially for rare kind of bacterial strains, is pretty expensive and challenging. You can't really do it. Another application is the kind of stuff I talked about yesterday at the AI for Vietnam event, kind of like in the sustainability space, trying to think about ways to use AI and machine learning to help address sustainability problems, and trying to understand poverty, hunger in developing countries like Africa. Again, it's a situation where getting labeled data is pretty hard, so you kind of need new techniques to get around the labeled data scarcity. So what is the holy grail here would be to somehow be able to learn how to solve interesting tasks using unlabeled data, right? Getting labels, getting people to provide labels for your images is expensive, it's time consuming, kind of like the cost will scale linearly in the number of data points that you want to label, roughly. But getting access to unlabeled digital data, it's pretty easy, it's pretty cheap. There's tons of images on the internet, tons of videos, lots of text that you can potentially use. And for example, in the kind of applications that I discussed before, in the sustainability space, another cool application area is satellite images. You get a ton of them, essentially an infinite amount, but the challenge for them getting labels, getting humans to annotate what's going on in these images is expensive. So the kind of like the grand challenge is how do you learn from unlabeled data? How do you figure out what is the structure of these objects? They're very high-dimensional objects. You can think of an image as like a big collection of pixels. Is there a way to teach a machine to sort of like interpret, make sense of what's the hidden structure in this very high-dimensional data? And so the one way of trying to do this is to use this approach based on generative models. And the idea, one way to, one metaphor that you can use to kind of like explain this approach is through this quote from Richard Feynman, the famous physicist. At some point he said, what I cannot create, I do not understand. He was actually referring to mathematical theorems. He was saying that until he basically can prove a theorem by himself, and he really understands he can derive a proof by himself, he really doesn't understand a mathematical concept. And I think we can kind of like take the contrapositive of this, and the idea is that if we are to somehow build a machine that can understand what an image means, or what some natural language means, or some speech signal means, then we should also be able to, this machine should be able to create new objects that have the right structure. Right? If I want to understand Vietnamese, then I should probably also be able to speak it, right? And or if I want to understand what is the structure or the meaning of a natural image, then intuitively, then I should also be able to kind of like draw one, or at least be able to imagine something like that in my mind. Right? If I understand the concept of an apple, then I should be able to imagine one, maybe sketch it. Right? That's kind of like the idea. If we want to build a machine that can really understand these complex objects, maybe one way to approach the problem is to try to build a system that can generate this kind of data automatically. And so typically the way this is done is using a probabilistic models. The idea is that you can start with a lot of data, which is unlabeled, which is kind of crucial, just images that you can prove from the internet. Then you can learn some kind of probability distribution, P of x. And the idea is that this x here is an image, is a collection of pixels, and somehow you train a model so that it assigns high probability to things that look like the images that you have in the training set. You should assign low probability to things that look like, let's say, like random noise. And the idea is that if you can somehow do this, then this is a generative model, because if you were to sample from this probability distribution, so if you were to set the pixels that compose this random vector x based on this probability distribution or this density, then you should be able to get things that look realistic, and crucially, they should be new. These should be things that new images that kind of look like the ones you have in the training set, but are generated from scratch, right? This is kind of like an imagination. This is like a creative effort where the machine is generating something new. It's generating one of these complex objects with the right structure, like completely from scratch. And there's been a lot of success in the last few years in building these kind of models. You might have seen these kind of images if you follow the generative modeling literature. Kind of like these are images that are synthesized by a machine, by a computer, by a GAN model, and they look pretty realistic to me, right? It's pretty amazing that you can build a machine that can generate these kind of images completely, essentially in a non-supervised way. Right? So they're kind of like the main way, as we saw before, in which these models are built are by looking at a probability distribution. And there are kind of like two main ways to represent the probability distribution. One way is to basically have some kind of explicit mathematical formula that will tell you how to map an assignment to all the variables in the model to some kind of probability or some density, right? And this is kind of like the formula that you use to specify a Gaussian distribution, right? That's an explicit probability model, because given any x, you can figure out what is the density that the Gaussian assigns to that particular point. And if you know this kind of literature, there are a number of models that are explicit, like pixel CNNs, real MPPs. If you don't know what these things are, it doesn't matter. It's basically one way to be able to represent, to specify these complex objects. Because the problem is that this function is complicated, because you need to be able to assign a probability value to every possible way in which you can assign these kind of variables. And if you have, let's say, n binary variables, you have 2 to the n different possible assignments to these binary variables. So this object is actually pretty complicated. It might take a lot of parameters to specify, it might take a lot of parameters to a lot of data to train. So you need some clever ways to basically specify this probability distribution in a compact way. The other way is it's an implicit kind of model, where the idea is that you kind of like specify an algorithm that will produce the samples for you, right? So you don't have an explicit formula for the density anymore, but you have a procedure that you can use to produce samples. Right? So it's a different way of specifying the same object. For example, you say, well, I'm going to start with some random uniform number generator, like what you would do in a normal programming language. Then you have some kind of program G that will take the randomness and will transform it in some way and will produce the sample for you. Right? So this is how you would code out some kind of function that uses randomness. So it uses some kind of random number generator and transforms it into an object. And if you code this thing right, if you choose G in the right way, you might be able to get the right effect. Typically, G is some kind of neural network. This is sort of like the strategy behind GANs, generative adversarial networks. You start with some noise vector, think of it as randomness that you inject into your code, into your procedure. You transform it using a neural network, and then you produce data, in this case, images of digits, let's say, that hopefully are realistic. Hopefully, they look like the ones you have in your training set, and there is a whole procedure for training this kind of models. So what I'm going to talk about in this seminar is an alternative way of representing these objects, which are kind of like the fundamental thing that you should be worrying about whenever you want to build a probabilistic generative model. And what I'll try to argue is that there are some advantages that we can get if, instead of looking at the probability distribution, P of x, or a density, we look at its gradient. Right? Before we were looking at P of x, that was kind of like the key object. Now we're looking at its gradient with respect to each individual. So it's kind of like a vector of partial derivatives with respect to each individual component of the density. And this is called the score. This is the gradient of the log density. And the intuition is that this is a function that for every x will give you a vector. And the vector basically tells you what is the direction in which the density grows the most. Right? So you can think of it as a vector field. If you have a density, we kind of like two modes, one up here and one down here. And for every point, you have a vector, which is just the gradient of this log density, and it will tell you which direction should I move if I want to increase the log density, if I want to increase the probability of my sample x. So you see here the kind of like point towards the modes. Here is just like here the color corresponds to the probability density assigned by the model to each point. It's a 2D thing, it's just an illustrative example, but kind of like there is a region here, there is a sign high probability, a region down here, there is a sign slightly less probability, and this is a density, and kind of like it's a way of specifying the object that we care about. Alternatively, you can think about this vector field of gradients of this density. And if you like physics, and you still remember some basic, very elementary physics, the analogy here is the same as if you think about an electric potential or an electric field, right? These are the same objects, and sometimes there's two particles, and there is an electric field. Sometimes it's convenient to think about the electric potential. Sometimes it's convenient to think about the electric fields, but fundamentally they really represent the same object. All right. So now, why should we care about looking at the score instead of the actual probability distribution or density P of x? So let me give you one possible motivation. What this looking at the score allows us to do is it allows us to use more flexible kind of probability distributions. One challenge of this, of specifying a probability distribution P of x, is that it has to be normalized, so it has to be non-negative, and it has to sum to 1, right? And in order to get these kind of properties, you need to be very clever about the kind of structure that you need to impose on the model. An alternative, very potentially flexible way of specifying this probability distribution is to define some energy function, f of x. This is terminology again that kind of like comes from physics. And the idea is that you input, which could be, let's say, represented by a neural network. You feed in values for the random variables, and then f of x will give you a scalar, which is basically the energy of this particular configuration, of this particular assignment to all the variables. Then you specify your probability density as an equation with this kind of structure, where it's guaranteed to be non-negative because of the exponential here. Then you have this object here, which is called the partition function or the normalization constant, which basically you need to ensure that this object that you have on the left, the probability distribution is actually it's valid in the sense that it sums to 1. So z theta here is basically the integral of this object over the entire space. Right? You kind of like need to figure out what is the entire volume of the space in order to normalize the problem. So the problem is that typically computing that partition function is very, very hard. This is a very flexible kind of probabilistic model, but you pay a price typically because the partition function involves some very high dimensional integral. You have to integrate over all possible values of x to kind of like figure out what is the total volume. That's expensive, and in practice training these models is hard. And this kind of like shows up here. If you want to, let's say, train one of these models using maximum likelihood, you have a data generating process P of data. You want to find the parameters theta such that your model assigns as high a probability as possible to the samples on average. If you look at this expression, you take the log of this, you're going to get a term here, which is easy to evaluate. This is just basically evaluating the output of a neural network. But then you have to normalize. You have to kind of like compute the log of the denominator, and that, in general, is hard to compute, which means that you can't really train these models efficiently using maximum likelihood. That's why they kind of have fallen out of fashion, and nobody's really using these models anymore, though they were popular back in the day, because they have this problem, this computational problem that estimating the partition function is in trouble. So, why are the scores useful? Well, if we look at the expression of log theta, it basically has these two components, it's the log of f and the log of z. Now, if we look at the score, remember this is the gradient, this is the vector field, the gradient of the log density. Now we take the gradient of the two terms. We just take the gradient with respect to x of this, the gradient with respect to x of this, and as you can see, this is a constant with respect to x, and so that disappears. So although evaluating the log density is hard, because it involves the partition function, evaluating the score is easy. It doesn't involve the log partition function. So it allows us to bypass the partition function completely. And so the idea is that if we want to learn a model of p data, we have some training set, like a bunch of images, we want to learn a model for these images, a generative model of these images. Instead of trying to learn them by maximum likelihood, what we can try to do is we can try to match their scores. There's going to be a vector field of scores for the data generating process. There's going to be one for your model, and a reasonable objective here is to try to make them as similar as possible. Because we know that they are essentially the same object, right? The density and the score are effectively the same thing. If we are able to match the scores, then we're also implicitly also matching the density as well. Right? So that's kind of like the idea. And the beauty of this is that at least we can compute the score efficiently because it does not involve the partition function. Right? So, and this also has a number of other applications, including VAEs with implicit encoders, Marshall standard encoders, and score-based generative modeling, which is what we're going to talk about. Right? So this leads us to basically the main kind of like technical problem that we're going to discuss today, which is this problem of doing score estimation. Right? So the idea is that there is some underlying density data generating process that we care about. We would like to figure out, to learn this vector field. How changing the values of the random variables basically affects the log probability under the true data generating process. And so there is this underlying data generating process. We would like to learn its score. But what we actually have is typically just a training set. Right? We typically just get samples. There is some underlying probability distribution of the data. We get to see some samples, let's see a bunch of images, a training set, and we would like to go from the samples to this vector field of scores. That's kind of like the problem that we're trying to do. Because if we can do that, then we're basically in good shape. This is exactly sort of like what we're trying to do here. We have samples from P data. We want to figure out how this vector field looks like. We're trying to match it to some kind of model that we have, which could be parameterized by a neural network, it could be an energy-based model, and we'll see that there are a number of other ways of achieving this. So, is that main idea clear?
So the problem is we need to assume that you can compute the gradient with respect to the x, which has to be continuous.
Yeah, so this is all continuous, yes. And we'll see that there are going to be some tricky things about data lying on multi-dimensional manifolds, and we'll see how to get around that later. But yeah, so here I'm assuming that everything is continuous, good point. And as we'll see soon, one challenge is that we need to figure out how to compute sort of like this thing when you only have access to samples, right? We never have an explicit formula for P data. The only thing that you see are samples. You only see images. So computing this thing is not going to be easy, and we'll see that there's a very neat kind of trick that you can use to get around that problem.
So you have any specific assumptions when you deploy this model?
So far, there's basically no assumption except that it has to be over continuous random variables. Other than that, it's very, very general.
So I guess for things like NLP, it's kind of hard to apply.
Yes, for NLP, it's hard. Yeah.
What do you lose by doing this?
We'll see that we lose statistical efficiency, basically. You can still prove that this is a consistent objective, and that if you have infinite data, you will learn the right model eventually. It's still, the estimator that you get is still asymptotically normal, so it has the nice properties that you typically get by if you were to do maximum likelihood, but it's not as efficient as maximum likelihood, in the sense that you might need more data to get to the same quality of the results. But the assumption here is that we have lots of data anyways, so it fits well with this kind of scores. Other questions? Yeah.
How can you calculate gradient likelihood of data?
Yes, that's the key. That's the key thing that's going to come up next. How do we get this thing right? There's a very neat trick to do that. So let's see how to do that. So the problem here is that we have samples, and somehow we want to compute the gradient, this gradient, like the score. We want to figure out how the density changes if you were to kind of like what's the direction that which you should change x to increase the likelihood as much as possible. But you only have samples. You never know P of x. And just to be clear here, our model is going to be some other vector valued function. It's another vector field. You feed in an x, it will give you a vector. And hopefully, kind of like the goal is to try to make this thing as close as possible to this thing and match these two vector fields. So how should we compare to vector fields? So remember, this is our model. This is the vector field corresponding to the data generating process. What is the right way of comparing to vector fields? Well, one simple way is to basically look at the different. Remember, we have a vector. There are two vectors at every point. At every point, we have two vectors. There is the true score of the data generating process, which basically tells you what is the direction that I need to move to increase the likelihood as much as possible. There is one given by our model, and so all over the space there's going to be two vectors. And we want to figure out how close these two vector fields are to each other. One reasonable thing to do is to just compute the Euclidean distance of these two vectors at every point, and then average. This is one way of comparing two vector fields.
Sorry, what is S theta?
S theta is going to be our model, basically. Before, S theta would be this thing, would be the gradient of log p theta. So it could be the gradient of some function of theta, but I'm just calling it as theta more generally. As any kind of function, it's basically, you think of it as any neural network that will take x as input and will produce another high-dimensional object, which is
move
another
from px to s theta.
Yes. Right. So this is going to be the objective that we're going to use. There's a data generating process P of x. We have a model S theta, and we try to make sure that on average over all possible x's sampled from P data, these two objects are similar. So the vector field of the true data generating process is similar to the vector field that we're estimating using our model. All right? And this is called the Fisher divergence. Now the question that came up before is, this thing, we don't know how, this thing is tricky, right? The only thing that we have are samples from P of x, and we need to somehow figure out a way to estimate this vector field. Right? And so it turns out that if you use integration by part, which hopefully you still remember from basic calculus, you can simplify this formula, and you can rewrite it in a way where it does not depend on the gradient of the log data distribution anymore, which is pretty neat. And it works like this. It's actually very simple, so I'm going to actually show you how this works. If we look at a one-dimensional case, just for simplicity, so here we have vectors, we have Euclidean distance. For simplicity, imagine that x is one-dimensional, so this thing looks like this. This is just the square of these two things. This is just a derivative. I'm just keeping it as a gradient, just for keep it consistent, but this is just the derivative of log p of x. Right? So the vector field is actually just a scalar. this case. So here we have something like the square of a minus b, and we can expand it, right? Well, I guess you can write down the expectation as an integral, of course. And then we're going to expand this square here, right? So the square of a minus b squared is going to be a squared plus b squared minus 2ab. It's going to be something that looks like this. This is just the square of the first piece. This is the square of the second piece. And this is the product of the squares, right? Now, notice this piece is easy to evaluate. We're assuming that we know how to evaluate x of theta, so this is something that we know how to evaluate. Notice this piece does not depend on theta. Theta are the parameters of our model. Let's think of it as parameters of our neural network. They don't depend on theta, so it's just a constant that we can basically ignore. And the tricky piece is this one, the red piece, which is just the double product of this and this. Now here's where we're going to use integration by parts. If you remember, the derivative of log p of x is the same thing as 1 over p of x times the derivative of the argument of the log. Right? You have the log of f of x is going to be 1 over f of x times the derivative of f of x. This is really just what's going on here. If you have seen reinforce or those kind of estimators, that's the same trick that's made there. And then you can simplify p of x, and you're left with something that looks like this. Right. Now, if you remember integration by parts, this is the integral of p prime times s. And so this is the same thing as ps evaluated at the boundary where you integrate. Minus, and there's a minus here, so it becomes a plus. Now you switch the order of the derivatives. Now it becomes the derivative of s times p of x. Right? Do you still remember integration by parts? Right? It's the integral of f prime g is basically fg minus the integral of g prime f. Right? This is the same thing that we're doing here. And the assumption here is that we can, assuming some smoothness conditions, this thing will go to 0 or it will be a constant, which is sort of like reasonable. If you make the values extremely large, the probability assigned by the model should be small. And so basically we're left with this, which is again something that we can evaluate efficiently. Right? It just involves the gradient of something that we know, and it's an integral with respect to p of x of something that we know, which is another expectation. Do I have it? Yes, it's an expectation with respect to p of x, which is the data generating process of something that we hopefully know. Right? So if S theta is a model, all you have to do is to basically take an expectation with respect to your data generating process, which you can approximate using a training set. Something, just evaluating the square of whatever is outputted by your model, and then just take the gradient of your model with respect to the inputs. And so kind of like that's the neat trick. Something that apparently looks intractable and horrible is it involves the gradient of this thing that we don't know, and we want to have samples from it. And it ends up being something that we can evaluate just using samples from that distribution, which is just a training set. That's kind of like a pretty neat trick that allows you to basically estimate the Fisher divergence just using samples. Did I go too quickly? Any?
Sorry, the beginning part of this. Is there a specific reason why you choose others in this?
Oh, yeah. So the idea is that the reason we use Fisher divergence is that we might want to use something like an energy-based model where we're doing maximum likelihood, so using KL divergence, which is equivalent to using KL divergence instead of Fisher divergence. Is intractable because it will involve the partition function. And so the idea is, the picture is that it's something like this. You have a space of probability distributions of the data that you have maybe parameterized by some neural network. Then you have p data, which is the actual data generating process. whatever generated the samples that you have in your training set, typically you would kind of like find the model in your model family that is as close as possible to the data generating process. And typically you would measure this distance using KL divergence. That would give you maximum likelihood. Here we're saying instead of using KL divergence, because we cannot evaluate it, we're going to use Fisher divergence, which is something that we can do. And it's a different way of measuring similarity between distributions, and but it's more suitable for this kind of sample. Questions?
One enhances, what does it mean to minimize this?
Yeah, so
Try to,
what does it mean to minimize?
Yes.
In what sense?
okay, so you started with the one from both.
Yes.
Intuitive, I can understand.
Yes.
Can you explain what exactly the last equation?
So
So you want it to be a theta to be small?
you want to make this thing as small as possible as a function of theta, because that means that basically the two vector fields are as close as possible to each other. And the neat thing is that this is something you can optimize. This thing is not necessary. And
Why can't I choose something as theta very small, 0?
then you might not necessarily optimize this thing.
That's what I'm trying to. If I make s theta 0, what is delta? Derivative with respect to 0 with respect to the data point, is that
It's
is that infinite? What is it?
well, this is your model, so you can choose whatever you want.
Let me choose it to be 0. Then what is delta x of 0?
Well, I guess that would be a constant, so that would be a 0 vector. I guess.
Okay, so you want something negative, so you just
Yes.
take it.
Yes. All right, so turns out that if you do it, so here we did the math just for simplicity for the one-dimensional case. Up here we actually have a vector. We have a Euclidean distance here, so you need to look at the vector version of this, which works out to be pretty much the same thing. It ends up being the squared norm of S theta, which is our model. And then you have this object here. Here we have the gradient of S theta. Now this becomes the trace of the Jacobian of S theta. This is how we basically generalize what we had before to the multi-dimensional case, which is the interesting kind of setting where you have more than one random variable, more than one pixel. This is what you need. And this is what's called score matching. It's not something we invented. I'm just reviewing existing papers. This is something that people have come up with before, and it's an interesting kind of like objective again because kind of like you can use it for energy-based models, and it does, and as we'll see, you can also use it for different other kinds of models, and it's a pretty interesting objective that I think has not been explored much in the literature. It's just another way of comparing probability distributions and have some advantages compared to probabilities. Now, and just like to make sure, kind of like in practice, you don't have P of X as usual. This is the data distribution. You only have samples, so you approximate it using a training data set. Just approximate the expectation with a Monte Carlo estimator, which is just averaging your samples, this kind of objective. Now, what's if we go back to the case of so before, I guess we kind of like introduced S theta as being some kind of score corresponding to an energy function. In practice, you can just have any kind of like neural network that will take as input x's and will produce a vector field, will produce a vector. This is kind of like if you think of these as being pixels in an image, this thing has to output another image. It has to have the same shape as the input. Right? So in fact, we use the kind of architectures that people use to do segmentation, to do kind of like dense image prediction, and that's the kind of architecture that you want to use for as data. It has to map an high-dimensional object to some other high-dimensional object. Now, if you look at that objective, we need to compute this thing, which is trivial. You can just basically compute it by doing a forward pass on your network. You just compute the output, and then you look at this squared Euclidean norm. The trace of the Jacobian is a little bit more complicated. The trace, remember, is just the sum of the elements of the diagonal. So the way you would have to compute the trace of the Jacobian is that you would have to compute the first output, then you have to back propagate to compute the top left element, the Jacobian. And then in order to compute this entry, which is the partial derivative of the function corresponding to the second output with respect to the second input, you would have to do other basically backpropagation. You would have to backprop with respect to that object. Then if you want to do the third one, then you would have to do another backpropagation. So the challenge here is that evaluating this term actually involves the backpropagation steps. At least if you do it naively, there are some arguments for why you can't actually do it faster than this. So it's not too bad in the sense that it scales linearly the number of variables that you have in the model, the number of pixels, let's say, if you want to do images. But it's a little bit tricky because we have to compute this thing many, many times during training. So we would like to come up with a more scalable way to kind of like get rid of this term, the trace of the Jacobian of the model. So how do we do that? There are two ways to do it. Denoising score matching, which was proposed by Joshua Benjo a few years ago. The idea is that instead of looking at the original distribution, we're going to consider a distribution that we're going to perturb by basically convolving it with some Gaussian noise. We're going to define this Gaussian distribution Q sigma, which is just a Gaussian centered at x with some standard deviation, with some covariance, diagonal covariance with standard deviation sigma. And then we're going to define a perturbed distribution, which is basically what you would get if you were to add a little bit of Gaussian noise to every sample from your original distribution. So you can think of the process as you first pick a sample from P of x, which is the object you actually care about, then you add a little bit of Gaussian noise to it. Right? You sample from this Gaussian, which is centered at that point, and you add a little bit of Gaussian noise to it. And if the Gaussian noise is small enough, then these two distributions are pretty much the same. They're quite close to each other. And it turns out, and it's proven in this paper from Joshua Benjo's group, that doing score estimation for the perturbed distribution is actually easy. Because basically it just involves an expression that looks like this, where you just have to evaluate your model, and you have to evaluate the gradient of this object, which is very easy because this thing is just a Gaussian density. So this term is basically very easy to evaluate. I'm not going to show you how to do it, but it's basically again integration by parts. And basically what happens here is what you do is you start with your sample, you add a little bit of noise, and you compute this quantity, which is easy to evaluate. Because remember, Q sigma is just Gaussian density, so this thing is easy to evaluate, and then this thing is just your model, so then it's easy to evaluate. So you can basically optimize this objective efficiently as a function of sigma, as a function of data. Right, everything here is easy to compute. The alternative is that something that we showed that we had a paper at UAI presented a few weeks ago, is to do random projections. So the idea is that sort of like a d-dimensional problem is tricky, but if we could somehow randomly project, we could project it down to a one-dimensional problem, then things would be easy. And so what we actually do is we just randomly project these vector fields onto random directions, and then we just try to match the projections on the randomly projected directions. So the idea, remember, is that we're trying to make S theta close to this true vector field, the true score. Instead, what we're going to do is we're going to take a random direction. We're going to project all the vectors along that direction, and then we're going to compare the projections. So we're going to pick a direction, we're going to project along that direction, and then we're going to try to make them similar along those respective directions. And I'm not going to go into this, but what happens is that, again, you can prove that this is a valid estimator. It's actually asymptotically normal, it's consistent, has all the nice properties, and you can compute it doing basically just one back propagation. So if you do one random projection, it's one back propagation. You can do more than one, and then it basically scales with another projection. It's not really super important, but it's just some way that you can use to make this attractive. So now, how do we use this to actually learn energy-based models? So remember that the nice thing about the score is that it does not involve a partition function, something we can compute efficiently. So what we can do is we can define a score, which is just the gradient of f of theta. Right? So f of theta is just an energy function. It takes x and maps it to a scalar. The gradient of that thing is going to be our score. And it's something that maps x to a vector. It's a vector field. And then we can try to, px becomes p data. It's just the data generating process. And then we're just trying to match it. All right? So, and then you can use either denoising score matching or slide score matching. And it works well on a number of benchmarks, but let me skip that. Let me talk about how we can actually use this to define a new class of generative models. They're not autoregressive GANs. It's a different kind of beast, a very different way of generating samples. So the idea is that we have some training data, which are just a bunch of samples. We can use all this machinery to estimate the scores. Then the idea is that we can try to effectively sample. Is this might be a video?
Maybe you can press.
Oh, yes. So the idea is that if we somehow are able to estimate this vector field of scores, then we should be able to directly sample. Let me play this video again. We should be able to directly produce samples from the model, and basically following the gradient. The gradient tells you which direction you should change your data to make it look more realistic, to increase its probability under the true data generating process. But to the extent that we're able to do a good job of coming up with this vector field, then we should be able to produce samples. But basically just following the gradient. You kind of like start randomly somewhere, then follow the gradient, and that will give you something that looks more realistic because it has higher probability under the true data generating process. And then you have to add a little bit of randomness because if you just follow the gradient, then you're going to get stuck. You're going to move around. If you want to sample, you actually need to add a little bit of randomness. And that's what's done using measurement dynamics. It's kind of like a diffusion process that you can use to sample from a distribution. And the only thing that it requires is just the score of the distribution. And that's the beauty of this measurement dynamics. Again, something close to physics. Basically, what you do is you initialize your sample randomly based on some proposal distribution. It can be uniform, it can be anything you want. Then what you do is you basically follow the direction of the score, follow the direction that increases the probability. Then you add a little bit of Gaussian noise. That's basically what allows you to kind of like move around. You don't get stuck in a local optimum. You kind of like get out of it and you explore different modes of the distribution. And the beauty of this is that it only requires the score. So we can directly define a generative model where the only thing that we do is we estimate the score and then we produce samples by using this measurement dynamics. Right? So that's kind of like the idea. We start from some data, we estimate via score matching the score, and then we use measurement dynamics to produce samples. And it turns out, we'll show you later, that you can get samples that look more realistic than what you can get with the latest GANs. Like you can get state-of-the-art numbers or the same exception scores on certain data sets by using this process, which is pretty promising because GANs are very hard to beat. But using this thing, you can actually get even better results, and it's a fully probabilistic model. It's nice, and so these good properties. So, what are the issues that don't allow you to actually? There are some technicalities that you need to take advantage, that you need to solve to get this to work. One problem is that if you're trying to sample from, let's say, natural images, it's actually the case that the distribution P data that you're dealing with doesn't really have full support. The natural images are structured, and they tend to lie on some kind of like low-dimensional manifold in this high-dimensional space. Right? And the problem is that if the data really lies on a low-dimensional manifold, then these scores are not really well defined. You would need to use covariant derivatives on the manifold, and we don't want to deal with that. So kind of like the intuition is that if the data lies on a manifold, kind of like these scores become bigger and bigger. They kind of like explode. Like imagine that the data lies on a ring, and you make the ring smaller and smaller, thinner and thinner, then the gradients explode. That's kind of like the intuition for why you can't really use scores in the ambient space when the data is actually lying on a manifold. If the data is actually on a small manifold, on a very, very thin ring, that has lower dimension than the ambient space, then the gradients are not really clear. And in practice, natural data sets, they do lie on low-dimensional manifolds. Here's an example. If you take MNIST, if you do PCA with, let's say, 595 components, the images are basically indistinguishable. If you take CIFAR and you do PCA with 2,000 components, again, basically the images are indistinguishable, which sort of means that the data looks very close to a 2,000 dimensional manifold, linear manifold. And if you allow manifold to be linear, probably the dimension is even smaller than that. Let me skip this. So the other issue is that the score that we're trying to estimate is going to be fairly inaccurate in regions that are far away from the high density one in the regional space. Right? The idea of this objective is that you have a bunch of samples, and you're kind of like using them to figure out in which direction you need to change them to increase the probability. Most of your samples are going to be coming from regions that are highly likely under the regional data, like close to the nodes, like something like this. But you never get samples from areas that are so like far away from the nodes. So the kind of estimates of which direction you need to move when your data lies far away from the actual nodes are going to be fairly inaccurate. Right? So here's an example where if this is the true data density, these are the true data scores, and you try to estimate them using score matching. In practice, it doesn't quite work. It works well close to the nodes, but then if you look at the scores, they're actually pretty inaccurate down here compared to the true ones. What you get is fairly inaccurate because you don't have enough samples. You never see points down here. So that's another issue that we have to deal with. Maybe let me skip this. This is another issue that arises. That basically turns out that Marginal dynamics kind of like mixes very slowly, and so you can't really use it directly when you have this kind of data line on the dimensional time. So the solution to these problems is to basically use a Gaussian perturbation. If the original data lies in a manifold, if you add Gaussian noise to the points, then the resulting distribution will have full support. And indeed, it has training. If you have this low, remember we have the problem that we have low density data regions. We never get to see samples here. If you start adding Gaussian noise, then the distribution that you get is going to be much more spread out. So you're going to start seeing samples kind of like all over the space. Right? And so the idea that we had is to basically use a sequence of distributions with different levels of perturbation. And we have the original distribution where there's no perturbation, but it's hard to deal with because of the products that is typical in a low-dimensional manifold. And you can add more and more noise until you end up with something that doesn't look like the thing you care about, but it's good for score matching because it's spread out, it's very easy to do. So that's kind of like what we do. Basically then what you do is you do the following. You kind of like do annealed measuring dynamics. You start out by sampling the distribution with large sigma. It's not the one you want, but it's easy to estimate and it's easy to sample from. Then you use those points to initialize a new Langevin dynamics with a smaller sigma. Then you do that again with even a smaller sigma, and eventually it does the right thing. Eventually the points kind of like end up being the two modes with the right proportions. So it mixes much faster because you have this sequence of distributions. So, and just to show you that, I think this one doesn't work. Can you click? Well, maybe it doesn't. But anyways, basically, this is really important. If you don't do it, you just do vanilla Langevin dynamics. It doesn't mix, so that half of the points are here, half of the points are here, which is not what you want. If you try this one on the right, you do this annealing process. What happens is that after a while, you see that the points move and they end up in the right spots, and you see that there are many more points up here than down here, which is what you would expect because there's more density up here than down here. So now what we do in practice is that we have, now for different levels of noise, we're going to have different scores. And so what we do is we have a single neural network that will take as inputs the sigma, the level of noise that you have, and will produce a score, a vector field, corresponding to that level of noise. So the idea is that this is just for computational reasons. Instead of having n separate, in this case 3 separate neural networks that will model the different scores for different noise levels, we're going to have a single one with a shared, with an input sigma that will tell you what is the noise level that you're considering here. And then we just train them using basically denoising experimentation, just like what we had before, where we try to make all these, basically we try to make it work well for all possible values of sigma. And you can just basically just define a combined objective where we're saying the network corresponding to a small noise level should work well, the network corresponding to the larger noise level should work well, and so forth. And we're trying to match the vector field for various levels of noise. And it works quite well. Here's an example of what you get if you run into several data sets, like MNIST, CLA, CIFAR. These are the kind of samples that you get. So you see that you start from random noise, and you follow these gradients. This is just like the Langevin dynamics that we were doing before in 2D, just to visualize it. Here now we're doing it in high dimensions on an image data set. So we're learning how to sample by using this process of basically following the gradients.
So what is the dimension of the image?
This is just the natural image, 784 for MNIST, Saturday, it's just the usual. These are the standard normal data sets, but there's no dimensional interaction. And what's nice is that if you look at FID and inception scores, for example, in terms of inception scores on CIFAR 10, this is actually state of the art. It beats all the previous GANs approaches, including SNNs. So that's exciting because it's the first kind of like non-GAN model that can get really, really crisp, really, really nice looking pictures, which is typically something you don't get when you use autoregressive or other kinds of light-based models. But kind of like the takeaway here is that across the different number of models, this score matching approach actually gives the highest inception score of 8.91, which is better than everything else. And it's not the best in terms of FID scores, but it's doing reasonably okay. It's not you can do a few things. Well, if you were to do, how much time do we have? 5 minutes. Okay. So maybe let me skip, but basically this is just showing that it's not memorizing. So this is a sample that is produced by the model. These are the nearest neighbors that you find in the training set. So it's not quite identical to anything that it has seen before. It's kind of like showing that it's generating new stuff. It's not just memorizing samples that it has seen in retraining. So now here are a few more examples where sort of like you see that the nearest neighbors in terms of Euclidean distance are not the same. This is the same for CFR. This is, this I believe this is in feature space. If you take a pre-trained network and you look at nearest neighbors in that feature space, again, you see that it's not really memorizing. It's sort of like kind of like the closest examples in the training set are not quite distinguished. And just to show another example of the fact that this is really not memorizing stuff, it's doing something very interesting. You can try to do in painting. You can start with half of an image, and you can try to use the model to basically to fill in the missing pieces. And the original image looks like this. And you can try to see what the model produces as you run different kinds of marker chains. And you see that it's producing some variety. It's not quite producing the same thing, especially if you see down here. You're going to see some examples where, for example, the hair looks like this, but then the samples that it produces are quite different. So it's not really memorizing, it's able to, it has learned a structure of this manifold of images, and it's learning to do something interesting.
So all of this is generated by energy-based model, or is it generated by an implicit model?
This is not energy-based, actually. We have just a network that produces a score directly, but it's not the gradient of an energy function. It's just directly, basically, it's a UNet kind of thing that takes as input an image and produces another image effectively, which is the score. But it's not a gradient.
So you can think about it as an energy-based model.
You could, but there's not necessarily an energy such that if you take the gradient of that expression, you get that neural network. It's directly mapping from Rn to Rn, which might not be the gradient of an energy. But you could do that, it's just the performance is slightly worse, and so we did it this way. But you could also do it now. So maybe if I have a couple of minutes, I want to just as a teaser, whether these results are any good, just ask more like a conceptual kind of question about all this kind of generative modeling field and whether it's really doing something, whether it's even a well-posed problem, and to what extent we can trust these results and to what extent they are good. And I think evaluating these results is actually pretty tricky. I showed you some metrics, but it's actually it's a really deep question. Like, if I show you, let's say I train my generative model on a data set where all the images are like red cars, blue cars, and red buses. Do you think that the models should generate a blue bus or not? Or if I have something like this, I have a white swan, a white pigeon, a black pigeon, should the generative model produce a black swan? Right, not so clear. More concrete. Let's say all my training images have two objects, different shapes, different colors, different positions. How many of you think that the generative model, and here I'm talking about a GAN or a VAE or your favorite thing, how many of you think that it will produce images with just two objects? Or do you think it will produce images with maybe three objects, one object? How many? Raise your hand if you think A. B?
We want B.
Yeah. So B is true. Indeed, it does generalize, which is, you see, what we want is not so clear. It's an interesting phenomenon that seems to occur, that they generalize. But clearly, sometimes you want them to generalize, sometimes you don't want them to generalize. And so it's pretty remarkable that we would like to understand which way they generalize. For example, if you have a training distribution where all the images have two objects, it turns out that and then you look at the counts of objects of the images that you generate, it turns out that they have this kind of log normal distribution. Interesting empirical finding. So they do train, and this is consistent across GANs, VAEs, and all different models. Now, what happens if all the images have 2 objects, or let's say 7 objects? Interestingly, it kind of behaves like a linear filter, and you're going to get distributions that kind of like, this is what you would get if you have 2 objects, this is what you would get if you have 7 objects, kind of like what you get is something that looks like this, it's kind of like a mixture of the two, which is something that looks like that. The most interesting thing is this, is what if you have all the images of 2 or 4? Now these 2 distributions become close to each other, you kind of overlap. And what happens is that the distribution that you get looks like this. It's actually peaked at 3. And so this is very surprising because the model has never seen an image with 3 objects, yet most of the images it produces have 3 objects. Is it what we want? It's unclear, right? And you know, we did this for many other features like color, size, location. There are some interesting patterns that emerge. It kind of looks like that. I think the most interesting is when you start looking at multiple features, right? Because what would you expect? Let's say that the images have, this is all with a clever data set, right? But then we did it on several other data sets. It's all synthetic, but it's kind of like consistent across data sets and models. Let's say that all my training images look like this. There is yellow and red spheres and red cylinders. You think it produces yellow cylinders or not? Right. And basically, we've explored what happens for several generative models. And what happens is that depending on how much variety you have in the training set, for a while we basically just memorize. It will not produce this kind of strange combinations. But then after a while, we will start to generalize. We will start to fill in the gaps. We will start to make up stuff that you haven't seen before, basically. And sometimes I think it's what you want, but sometimes it's definitely not what you want because you can start generating, I don't know, dogs with 6 legs. That's probably not something you want, right? But how does it know what to generalize and what not to generalize? So I think fundamentally the issue is that we know that unbiased density estimation is impossible, and so you really need to introduce inductive biases, and so you really need to understand them better. And that's a potentially interesting direction for future work. And yeah, I think this is pretty much what I wanted to talk about. As expected, I didn't get to talk about how to use this stuff to do learning with limited supervision, but I think hopefully you got a technical talk as podcast. Some pretty pictures, and I hope you enjoy the talk. And the papers on archives, so if you want to learn more about the details and proofs, please look them up. Thank you.
So we have time for maybe 1 or 2 questions.
Yeah.
So in the last few slides, we described the generalization property of these models. Is that a function of your hyperparameters?
Not much. No. Surprisingly not.
So it doesn't matter how large you allow the gradients to be?
Like even the convolutional versus fully connected, even that doesn't even matter. Very surprising. I mean, you can find it. Of course, we didn't try everything, so I'm sure that if you really bad hyperparameter choices will break it, but reasonable choices, we did a pretty thorough kind of grid search, and we found pretty consistent kind of patterns with different kinds of GANs, W GANs, regular GANs, convolutional discriminators, fully connected ones, and it seems to be gradient penalty without gradient penalty.
Can you go back to the slide of the numbers of objects?
Yeah.
So from the perspective of we care about physics, connectedness. So I'm not sure how the definition of your is find that figure. I haven't read it. But from our perspective, A is the better is still possess the very basic fundamental features But these like how does it work like in the past like what is like characterized colors outside the objects with a shape?
So it's not clear.
Yeah, so it's just a little bit of feelings like these are is a small bit from another perspective. How we formalize generations.
Yeah, I think I'm not sure A is actually a better choice, right? Because the model is forced to generalize at some point. Because if you imagine, here I'm just looking at one feature like count. Now imagine you have count, you have color, you have shape, you have location, many different features. You have an exponentially large number of combinations of things. Your training set will only have a few of them. And now you need to figure out, should you generate a combination that you haven't seen in the training set or not? Your model will have to make that choice. Because either it remembers the training set and then it's not interested, or it has to generalize. And it's not clear to me what kind of generalization we want.
Okay, in terms of questions, what is the representation? It depends on how is the representation and then generations.
Yeah. So it's very hard to evaluate generalization if you do it in pixel space. So what we propose is to basically look at these semantically meaningful kind of like directions like count, shape, color. People that have used in the cognitive psychology literature. And actually, the interesting thing is that these findings are actually consistent with cognitive psychology. That this thing, this process here, of actually choosing 3 as the highest, is consistent with something called prototype enhancement. It's this idea that, like in your mind, you have a concept of what a mug looks like, right? You've seen probably hundreds of different mugs in your mind, in your life, and then you have a prototype in your mind of what a mug looks like. And cognitive psychologists have done experiments to kind of like figure out what is this prototype that you create in your mind. And it turns out that it's not one of the objects you've seen. It's some kind of combination of all the things you've seen, but it's not necessarily any particular mug that you've seen. So it's kind of like what happens here. You're not really remembering 2 and 4, but it's kind of like something in between all the various objects that you've seen in your life. Even though that particular prototype that you have in your mind is not something you've seen. It's not something that exists. It's some kind of strange combination of the objects you've seen. So that's what we would call it prototype enhancement, because it has the same kind of flavor.
If you have more data,
that's something that we didn't explore. That's a good, like we always assume this is synthetic, so we can generate as much training data as we want. And so we didn't explore the angle of how does that affect generalization. But that's a good question, because the count, of course, should matter too. And but that was tricky, kind of like to explore. But that would be, so we kind of like put ourselves, just to remove a confounding factor, we just put ourselves in the situation where we have infinite training data, basically. So it's really all about the adaptive bias of the model. But that could be an interesting extension of this to explore how is this a function of how many examples you see. I think that'd be quite interesting. We'd probably do it.
So I have a question. For this kind of models, is it possible to estimate the likelihood just for evaluation purpose, for example?
You can have some of them, unless I guess we did pixel CNN also. So for at least that one you can. For VAs you can get lower amounts.
Okay. So for this kind of model, at least you can get an estimate of the likelihood and perhaps you can compute complexity of it.
Yes.
Related question, when you do the score matching to the generated sample, when do you stop?
Good question, yeah. So we have like it's kind of like hyperparameter, the number of steps. In principle, these are macro chains, so they will move from one mode to another one. So
But wouldn't you collapse to a few modes if you keep doing so?
they kind of, this mix is very slow. So what happens is that once you make the noise basically small enough, then it tends to stick there. Then if you crank up the noise again, then it moves out and it kind of goes to a different mode. And so that's one way in which you can kind of get diversity. But still, yeah, basically mixing is pretty slow, I think. So you don't actually get to see that, or it generates this phase and then it moves to another phase. You don't actually see that. So it's more like using this score as a direction that points you to the manifold.
So you really mean that it's a lot of modes, a lot of place, very, very flat, somewhat.
Yes. This is what we're gonna do. You can kind of think of it as you kind of like there's this data manifold, and you start somewhere. This core tells you which direction you need to move to get there, and then once you get there, then you don't really explore it actually. You kind of like find a point, but it's not one of the ones you see in the training set. So that's going to be interesting. Where is the structure? You kind of like see stuff, generate stuff that you don't see.
All right, so please join me in thanking Stefano again for a good talk.
I have one more question. You have room for it? Yeah, so what is the next step that you try to go further, like how to generate generalization?
Oh, for generalization, that's
What should we work on?
well, I think what the gentleman that was saying about like training data size could be an interesting direction.
If you increase the size of the data sets, then I think you can become a valuable.
Do you think this one can work for NLP things?
I think there is definitely an interesting space there to explore. I think defining the features would be a little bit harder. Images are there's a much richer kind of like literature that you can define.
Do you see like try to work on that topic?
I know personally I'm getting work on evaluating NLP in terms of diversity and sample
You
quality.
said that? Who?
Personally, yeah.
Yes.
So kind of like diversity versus sample quality.
Okay.
Because you can always just memorize the stuff you see in the training set. You get perfect sample quality, but there's no diversity.
Right.
And so it's kind of like getting at the same question: is do you want to generate new stuff or not? And how do you trade off generating new things versus generating high quality? It's not the same thing. It's not exploring in different directions, but I think it's kind of like looking at the same problem. Yeah. Is the right evaluation? It's not clear.